So next one we will go to the deep learning field. So we take step by step. We learn from the Bayesian whole model, from how you use the Bayesian model to identify the physical laws, and then go to see how to use these machine learning models from your data, especially deep learning through neural networks. All right, so take your time, just treat this as a learning journey with us. And then we go to the next talk on the deep learning for material synthesis. This study we have developed in my group together with PhD researcher Jiali Li. Later on, he will introduce all the details of his work. We aim to use machine learning methods to accelerate the gold nanocluster synthesis through the combined neural networks. So you will see this gold nanocluster synthesis to be a very important field in the material development. And many of you may be domain expert in this field. So we collaborate with our experiment researchers together to see how we can use these tools to further accelerate the understanding and the synthesis process. As we all know, when we do the material research, many of the experiments are not at the steady state. They're even very far away from this equilibrium state. So how to understand this process is still a key issue to stop us getting into the fundamentals of our materials experiment. A lot of this trial and error, a lot of this guys in the process, especially when we consider the reaction systems, reaction conditions. Although you may have a lot of fancy set up experiment equipment in lab, but still when you design these experiments, it's a lot of human interpretation within it. So we don't have these first principle models available yet. You can be a super genius to develop those, but still we lack such understanding of the system. And how we can get the optimal synthesis rules is a motivation for us to conduct this study. If we got a lot of data from experiment, either successful or failure, how we can use this knowledge, this history, this data to equip us to further develop these optimal conditions. So before we go to a case study, I want to introduce you the machine learning tools. So these are the basic knowledge that for you to bring everyone to the same page. So we know that for machine learning, we have all different categories. The most commonly seen one are the supervised learning, actually. So it's basically you got the data and you label this data as a series of these label features. In machine learning, you can call it features, or you can call it just those X, the features of the data. And then in materials, they can call it materials descriptors, and some of the biostatistic applications, you can just call it some of the descriptors for the data input. And then you label the output Y. You link all the input features X to the output label Y. And through this, you have your training data set. And then through the whole data set into this kind of the black box machine learning model, can be a neural network, can be some other statistical models, and then feed this model to best describe your data. And this is called data training process. This training process gives you this supervised learning because you have your Y there. This Y is your labeled Y. You try to define what is the input X, leading to the output Y in this supervised way. So it's basically create this virtual model that can relate all those labeled input reaction conditions to the output material properties in this case study. So you got different repeated experiments. For each condition, you label it X, and then got the Y to be it's a successful experiment or not. So this is a labeling process, and you train the model through this supervised learning. So this is mainly used in the talks today we'll introduce. But for general machine learning beyond supervised learning, it's also a lot of unsupervised learning methods. So those methods have been there for decades. They are basically statistical methods, like the principal component analysis, those methods you may heard of. So those supervised learning basically has no output label Y. It has a lot of data points, and then train such model to give the different points into certain clusters, to different clusters based on their similarity or other statistical metrics. So this is how we define the unsupervised learning. Identify the trends in those unlabeled data. So we have no Y here, no this label, but we got the data points a series of X and then cluster them to different groups. So these methods, some of you from the ECE background, you have seen this probably in some, when we monitor the process or do some anomaly detection or some of the fault detection, we use these methods a lot as well. And also another rising category of methods, we call it reinforced learning. So this reinforcement learning is basically considered this learning person or learning thing as an agent, this machine as a learning agent. In the meanwhile, it has this agent-environment interaction. So it has an action and has feedback from the environment and has this reward based on the policy or value. So this method, this agent-environment interaction will allow this machine to improve on the job and with a real-time learning process. So this is like the AlphaGo. It's kind of the machine, how they learn in the process. So this is reinforcement learning. Okay, so this is just an overview, and we focus a lot on how to use supervised learning to guide our materials research nowadays. Okay, so I give you from very beginning. So we have this artificial neural network, ANN, you might have heard the term. So how does this work? So neural networks are showing a lot of power nowadays, but its principles are relatively very simple. Just mimic how human brains think. That's why it's called a neural network. So think about how our humans process knowledge, process information. When you see something, when you got something, the information sent to our brain. We have the neurons in the brain that get the signals in and then process it layer by layer. Although it's still some unknown system, but we simplify it through each neurons and do the basic processing. So assume you got the X, all the inputs as from X1 to Xn. So these are the outside inputs to you. And then with this series of inputs, just a linear combination we have all learned using the different weights, W. So if you add this W, X, I, weight them together, it will form a linear combination of all the inputs. So that's how the human brain processes information on the first layer, and then add these bios, this B here. So this is a linear combination of information. Then with certain activation function that has a series of functions for us to choose to activate the output, to make it nonlinear possibly, we got the output Y. So this is how one neuron works, both in our brain and in the neural network processing. With this, we extend each neuron to a series of more complex structure, because if you only process this, it's very simple, but it won't give you a very good fitting performance. But when you combine the neuron in this different framework, it gives amazing feature corresponding to different applications, different data structure. So here I give you some examples. The feed-forward neural networks are most commonly used. It just consists of a network of those fully connected layers of nonlinear nodes, or can be linear, but normally we need the nonlinear to fit complex data. So we got this data structure for each neuron. It follows the same processing information, process steps we have shown you just now. But when it's connected to a deep structure, even 2 layers, it can give you some amazing performance. And like for AlphaGo, some applications, when it increases to 7 layers, this magic layer number gives very good performance. But you can imagine that for one neuron, it's very easy to compute. But when you increase the layer, in the examples we gave you, when you try it later, for 2 layers, it takes time to run. So it requires very advanced computing resources to run the model. We also have more advanced different structure for neural networks, like the CNN, convolutional neural network. This is also obtaining a lot attention recently because they have shown so good performance in imaging processing. So when you got the information, the input data to be image, this large pixel information, the CNN plays a very good function to identify the image and then to get some of the nice features for image recognition. And also for another type of data, like the sequential data, when we consider those natural language processing, when I speak something to identify the sequence of the speech, or when you get time series data for weather forecasting, for example, or for your reaction pathways, we'll use this recurrent neural network. It's still a neural network structure, but it got a time step there to connect each time step, each T, into a model with another additional operations to get a new structure. So those are advanced structures of neural network. You can create your own as well based on what your data look like. With this, very good performance can be obtained through a training process. So this is a basic structure, but why it's important, how do we really do the machine learning tasks? And how the new feature about deep learning, as we discussed, when you increase the layer, it becomes a deeper framework. So when you have more of those hidden layers, the information processing will be more complex. And then the whole, it's still like a regression model, but in the end, this black box regression model gives you very good fitting performance, describe your data features. Okay, so this deep learning really means using a neural network with several layers of the nodes between your input and output. So it's more like the human brain process information. Our brain has tons of these neurons inside. So you don't just use one neuron to process information. They're all interconnected. So it's generally better, gives you better performance than this simple structure when you have this deep neural network. But for deep learning, we also have a lot of parameters within it to be tuned. I just walk through this quickly to see how we train deep learning model. It's multi-layer perception. So we have this X as our input, but this can be your data feature, or just you can throw data to the model directly. And then you got the weights. So how big are those weights are? Those are some of your hyperparameters you need to choose and train it. And also for what's the finally activation function, which means how do you finally decide your either classification task or your regression task. Those are the activation functions, also something you need to choose. Okay, so it seems good. It's easy to understand in framework, but when you really do the task, it's a lot of parameters to tune, to train, and you also need to sometimes design your own framework. And how do we tune those parameters? So this is a joke. In the end, every deep learning or machine learning researcher becomes like the parameter tuner. So when you grasp the basic knowledge, you will just rely on increasing your computing power to get better parameters, to get better performance. But still, we have some tools to help us to better choose this best model for our specific goal for the data. So we have a lot of different activation functions. So the functions can decide whether we choose this data to be 1 or 0, or how we regress the final output Y. And also we can use some of the linear functions or some of sigmoid or ReLU functions in this kind of shape. These are commonly used activation functions. So those weird names, if you do machine learning tasks, you'll be very familiar, you'll be friend of those functions. And also we need to train those multi-layer perceptions, how many layers you choose, how many epochs will you need, like the repeated cycles of learning, and what algorithms you finally choose to find the best parameter, because you need to search a parameter space to find the best one that gives you best performance and to define objective function. You will hear some wonderful examples later on. I just give you an overview of the fundamental knowledge, so you will learn more from the examples later. Therefore, based on this machine learning techniques, we will have a lot of opportunities in our material research field, in our accelerating material development. It's all different pillars. We can really use these tools, either for descriptors engineering to develop the tools, or to further use data augmentation to give us more of the material synthesis data. And we have a lot of these packages, because we give you all the data in like a very easy to use environment. But if you go deeper, if you're a professional user, to see deeper in the framework, you have a lot of these packages we normally use for machine learning tasks. So here we choose Python, which is also now the common platform. I think MATLAB also promote their tools. It's even easier to use. Just click the button and run. But it has certain limitations. So we always suggest our own researchers to go to the open source Python. We always publish our data together with a paper, so you'll be able to repeat the results easily. You no longer generate those results published on Nature Science that cannot be repeated. So nowadays, we will help you to encourage you to go to the open source feature to share the data and the code. Okay, and also R is very good in conduct a lot of this data processing or even visualization. So if you are following our talks today, you will be able to use many of the code we distribute to you and develop your own using the packages in future. But also nowadays, a lot of AutoML packages are available. So for non-domain, non-computing experts, You can just choose some of these auto machine learning tools that are able to help you to tune the parameters. So we tried several of them, like AutoVika, those kind of things. It's also based on into your Python code, but can give you very good parameter tuning performance.